A ray of sunlight shining straight on my nose. Oh, well, that will move. Anyway, so to continue what we were doing last week, so we were talking about various basic pieces in the enumerative theory of maps, and they come in different flavors. And so maybe I remind you that we were particularly focused on this one. And then today we'll be more talk about this kind of thing. And what sets them apart? So these are integrals over for some open set in the space of maps, and so therefore they require localization to define. So this one needs a localization to define them. So maybe I'll indicate that localization here. So, and what sets them apart from things like this or things like that, so which are not an opal. This still may not be exactly proper integrals, but still they not often explicitly some open set. Is that these guys are rational function, turn out to be. So this is not obvious, but this will be prove them that these are typical rational function of all variables. Most importantly, it's a rational function of the variable z we weight these maps by z to the degree. Z is some multivector, some variable. Z sits in Z is an element in peak X times C star. And so this series are both born. They're born in well, yeah, okay, got to be. This is the reason Bill Gates got the National Medal of Science or something like this. That this, his creation works so nicely. So they, right. So these are both they both this and that. Both born as both by definition they're sums or some kind of d's, z to the d times maybe some rational function of other variables, covariant variables. So because we sum over maps of all possible degrees, and the z keeps track of a degree of the map, and then we integrate over some moduli. We take some case theory, some Euler characteristic of some modular space of maps. That Euler characteristic in all the covariant variables will be a rational function. But since it's a finite dimensional algebraic variety and so on and so forth. But so this series, this has different fates. On one side, it's a rational function of z, and if it's a rational function of z, it also, therefore, it can only have so many poles in the covariant variable. So this would be also, well, I guess, makes sense to reason that it will also be a rational function of covariant variables. Whereas on this side, it really, so this is rational, whereas on this side, it's more like hypergeometric. And we spoke at length about this one. This is if you not at length, at some I gave some introduction to what this function would look like, and so that was more. This is this guy here. That is in some disguise was this elliptic stable envelope if you normalize it correctly. Envelope in a bit of disguise, but if you take that disguise away, that's a really elliptic stable envelope. And this is, and so we will talk about this one today. This is the fundamental solution. Certain Q-difference equation. Equation in all variables. So that is, so this will be, this is the topic. This is the focus for today. In fact, we'll start talking about that. So we will not exactly finish today, I don't think. So this is okay. And so I was thinking about this this lectures. I was in my head going over about how exactly all these things are proven, and this what there's a philosophical conclusion which I want to share with you, is that in fact there's all the statements are proven when all statements of this kind, they require at multiple times a geometric input. It's not like you prove some geometric statement. Like for example, suppose one can imagine maybe you can prove that one of these pieces is, let's say the one we talked about, this vertex is descendant. Let's say you prove it is an elliptic stable envelope, and then from there we purely formally by general theory of quantum groups, you deduce the rest of the statements. And I don't know an argument like that. And in fact, so it has to be separate geometric arguments need to be made at several steps. And I think this is I think it's good because this means there's real synergy between geometry and representation theory. Otherwise, you don't just prove one geometric fact and then reduce everything else by just formal manipulations. By formal, I think very highly of representation theory. I want to talk it down, but it's the fact that you have to make both algebraic representation theoretic arguments and geometric arguments, not once, but a number of times. I think in the end, I think that's a good feature of the subject. Or maybe that will change. Maybe somebody will think of some overarching fact that proves all the statements, but I'm not that one. I'm not that person. And the way I'm going to present you the story is that there's really separate arguments that lead to all these conclusions. And these arguments always have. So I will not go through any of them in detail because they all have a certain structure. And the structure is that there is always a soft argument based on like degeneration or localization. So we've discussed two features of this count. Is that one is that they satisfy the degeneration formula, and another they satisfy there's localization. And so this is both of these are modulo the technical foundation of you define the moduli spaces and you define the virtual fundamental virtual structure shift and so on and so forth. Modulo that, those are kind of soft results. And then, well, I mean, but there's also in each one of these arguments, there's a part which you need to prove that something's zero, or something is, maybe there's something or something is explicit. Usually explicit means zero, but sometimes you can also be explicit, not zero. And those require you to somehow require you to really look closely at the modulus, the actual numerator problem, and you have to make sure. But it usually follows some sort of rigidity argument, and rigidity argument, the way you set it up, you have to set up some numerator problem, and about which you prove it's a proper count, and then you prove it's well. So rigidity argument has two parts. If you do make it in, if some of you know very well, is if you make it in elliptic homology, then you have to make the case that this is something is a proper count, and then but so it's a regular section of some line bundle, but then you estimate the degree of that, you compute the degree of that line bundle, you show it zero, but show that line bundle is non-trivial, therefore it vanishes. And if you're in a covariant case here, it's a similar argument. You prove again. You start with properness, and then you see that this has to be Laurent polynomial, and then you have to compute the Newton polygon of that Laurent polynomial, and then you show it's in fact either it's a point, in which case it's some sort of monomial which may be able to compute, or it's in fact it could be not even a point, could be an empty set, in which case it's zero. So this is that's the general line of argument. That second part requires to actually look into what the numerature problem is, what the players are. That requires some kind of examination of the moduli spaces, and that's well, anyway, we will this require a little more detail than it's reasonable to present in the lecture. So there'll be parts which I'm not going to present in the lecture. But what we will today we'll talk about maybe the soft part of where the difference equations come from, and we will start with difference equation. Start here. Start with difference equations. In equivariant variables. These are because the way the subject is currently the way logic of the subject is currently works, you compute those first. So this compute. First, according to in the current logic of the subject. This is of course a very time dependent statement. Maybe somebody will have a different strategy how to unravel this whole knot, but the way I'm going to present today is this. And so where the covariant parameters live, first of all. So the covariant parameters, so we have some Rx. So X was maybe Hilbert scheme of points or an Nakajima variety. So let's say AG is Hilb C2N or an Nakajima variety. And so it's written, it's a quotient by some group. So it's a quotient. It's of the form, so X is maybe maybe there's some sort of pre-quotient. GIT quotient by subgroup G. Okay. And so the symmetries of that are this this means when this has some action means here we act an action of some bigger group G tilde acts here, so in which G is a normal subgroup. Maybe I'll write like it is a normal subgroup. And then there is a quotient, G automorphisms 1. And so this is where the covariant variables live. So most of the time, this G tilde really splits. So, but in terms of like it does for Nakajima varieties, and we have reductive groups, and so it's hard to find non-trivial extensions. But for the discipline of thinking, it's better to think that this is it's better to remember what is sub, what's the quotient. So this is what. And so as we were setting up the counts, we were thinking that we can also count, in addition to quasi-maps, we can do twisted quasi-maps. Quasi-maps to X. And so what are those? This is the data is you get it consists of, maybe I write P tilde. This is so if I have a twisted quasi-map from some source curve C to X. So this is the data of you take maybe P tilde. So this is a principal G tilde bundle. So this is you allow a twist not only by the gauge, but not only by the group by which you question out, but also by the group which acts. And so which in that bundle that of course projects to some, this kind of goes to some particular P out, which is this may be fixed. This will be allowed to fix, but don't. And so this is the difference between two different bundles, that two different G tilde bundles that give the same tradition, have the same tradition function modulo in the same, yield the same bundle of the automorphism. That would be exactly the difference. That would be the difference will belong to the group G together. So together with a section. The section, so you take S C going to the corresponding take the corresponding G bundle, X bundle. Pre-quotient. And then it's stable if it evaluates, so that evaluates twisted stable. And so stable means it evaluates to stable point. Away from. So to have an example, let's say we had ordinary quasi-maps. Quasi-maps from C to really, so example, from C to the Hilbert scheme of C to N. This was the same as PT moduli spaces. So maybe I don't need the brackets here. This is PT moduli spaces of, you take C2 cross C, right? But then there is an action of GL2 here, and we can use this action to twist that product. So this would be saying, if we take the twisted quasi-maps, this is now the PT theory of some, maybe I write, forgot what I call the threefold, maybe call it Y. Y, this is projects to C with the fiber C2. So it's a fibration. So you use use this GL2 structure here to twist that bundle, right? So in particular, the examples, the examples that I've prepared here are, well, I guess I prepared the DT examples, but you can imagine that the same. So let's see if I can select them both. And so this is some sort of DT. This is a valid. This is a DT configuration for well, maybe let's say P1. It's a little bit ambiguous what goes along my horizontal line. Let's say P1 cross C2. So this is my C2 here. This is my C2. And then, well, the way I prepared it, so that's already non-singular. It's already non-singular at infinity. So this is non-singular at infinity in my P1. And then instead I can take, instead of a direct product, I can take the total space of O of 1 plus O over P1. And so should I draw this? So maybe, how should I draw O of 1? O of 1, well, maybe the way to remember it is if I have, also remember the weight, that if I have a triangle, this is a picture of P2. And if I take them to my triangle and I raise it, and I raise a vertex, then this is P2 minus a point, and then P2 minus a point, that's the total space of, now I can project along that point, that projection along that point, that would be the total space of O of 1. And moreover, if I think how the equivariant parameters, is going to act on this. So for example, for instance, if my along P1 I act by with my torus of automorphism weights scales it by Q, then I can make it the same. So if I just Q scales the C, so if this is, say, maybe this is the origin inside C2, and Q scales that means Q would act with the same weight here. And then, well, since this scales this P1, this would be, he would act with Q inverse, and he will not act at all. So this would be here, this would be kind of Q to the 0, right? So if I want to know how, if I have a bundle O of 1, if I'd like to know how the transformation of the base act on this O of 1, then this is the picture. And it's one way to linearize it. Of course, I can linearize it by any other power of Q, but it's I'd like to, at infinity, since at infinity would like everything to be trivial. I mean, trivial in a good sense. Then this means this gives the, for us, this gives the kind of the preferred linearization of this of O of 1. And so now we're going back to this picture. The reason I have this angle here that will translate into the way to think about it is that you should really translate in these boxes, you can write an angle like that. So maybe, so this is, if this were the, if my weights of this action maybe were T1 and T2 here, and then Q along here, and then maybe Q inverse along there. Then in this new picture here, I should think of this as if my bundle is to be trivial at infinity, then I'd like this axis to remain be T2, trivial, and with the correspondingly trivial action of automorphisms at in the fiber of infinity. Then here, this will still have the action T1. Then along this axis, this will be Q inverse. Here it will be Q. Here it will be still T2. And so now the most important thing is that along, so maybe the most important thing I need to find a maybe that this axis will change. So this axis will have the weight Q times T1. And that's and so this is the geometrical. So in other words, geometrically having taking equivalent variables and shifting them by Q, that is what it means. So we take this shift. So this is we take. So it means if I have so this is the shift to equivalent variables. In other words, if I want to shift variables by shift happens by the value by Q applied to by sigma applied to Q, where sigma is some co-character of my group. Well, in general, let's say general G. So this is co-character. And we use sigma as a clutching function for a non-trivial X bundle. So the summary of the discussion is that if we want some sort of geometry to go with the take equivalent variables and I shift it, and I want some geometry to go with that, it's the geometry of non-trivial bundles over P1. Does that make sense? And any questions about that? All right. So now we would like to see so now we would need to actually see how this change affects. How does this change affect the sum? So we can define. So this means we can define. So it means we can define both. So I had an example. So well, actually, maybe I should think of some good notation for that. But since I didn't think of some good notation, but let's use ad hoc notation. I'll work on that. So you can have both. This means this is. We can define both kinds of counts. So this would be, this means a P1, which we glue non-trivial. Actually, glue non-trivial over this. So this means it's non-trivial. X bundle. So instead of, and then we can also do the relative thing. Of course, it's going to be the same. And we would like to see how this compare. So somehow a question I would like to ask. How do this compare with the untwisted count? So, okay. So, it's a question. And the first observation is that combinatorics, so the combinatorics is the same. Or the actual moduli spaces, or even if you think of the actual moduli, in fact, actual moduli spaces. So it's not just combinatorics is the same as if I insist that nothing happens at that entity, that at that entity I can just take my dot and just twist it. So it's clear that there's an obvious bijection between the two sides. So there's no there's somehow geometrically it's the same. There's no, right? For every configuration on the left, I have configuration on the right, and this is moduli space combinatorics really the same. But the way it affects the weights, that would be the kind of the weights are the different. So this may be and I remind you that the weights, since the moduli space already, so combinatorics, the combinatorics and the moduli spaces, the reason we somehow cavalier about identifying the two is that these counts are defined. This counts defined localization. I remind you. Defined using localization with respect to this, C star Q. And so this is really the this fixed loss with respect to the Q. What are they? It means you have something at the zero, and then you have just a kind of a straight edge, and that combinatoric is really the same. It's really identical. The way, however, the weights are different, but in a very controllable way. Which we will discuss. We will just discuss presently. So what are the weights? Actually, what's the weight? So this is we didn't have a proper discussion of localization formulas in either of the situations. So I will have a little bit of that, and then you can. There's a good written sources. There are good video sources. Maybe I'll send some pointers in this course chat for those of you who are not familiar with the subject. But so what does it look like? So if I have a brief discussion of localization. And so this is of weights and localization. And let me have it. Let me have this discussion. This sort of in this DTPT situation, which is the quasi maps. It's really the same. So let me do this in DTPT. So just for concreteness. So if I have or doesn't have to be. So it could be, instead of DTPT, you can think of a category. So maybe if so this is we're doing maybe E. So this is an object in the Abelian category. Category of the kind you take the kind sheaves threefolds or sheaves or maybe quivers, representations of quiver valued in sheaves on my curve C. So that would be the quasi map to a quiver. You would talk about like the corresponding. You can think of a moduli point as you have a bunch of bundles. You have a bunch of bundles on the curve, and then you model it in maybe curves, vector bundles. My curve C and maps between them. That's a quasi map. That's a quasi map to my so that's a quasi map to my X, right? To my vector bundles and so forth. And then if you think of virtual tangent space to the moduli at this point E to the moduli, this will look like, so what would look like? This will look like, first you have a moduli, you consider objects modular isomorphisms. So there's always some kind of infinitesimal isomorphisms plus deformations minus abstractions. Well, and then who knows? So usually you hope there's nothing, no higher abstractions, and you wanna kill this by we want this to vanish for stable, E stable in some sense, and then we would want this to vanish by some sort of duality, some certain type duality. And so if I have an object in like a category of sheaves and so forth, then this will start minus the home from E to E plus deformation would be X1 from E to E. The abstraction would be in X2 from E to E and so forth. And so if you think that if you really think that this is really zero, if really zero, then this would be minus the Euler characteristic of EE. So minus the alternating sum of all x. So if I have a, so this could be, so this would be, so in particular, this would be accessible. This is really, it's really accessible. This is. So if we compute, in other words, if we would like to know what is this Euler characteristic as some object, so it lives in K-theory in two senses. It means if you would like this Euler characteristic, know what it is as a virtual bundle over our moduli, that's some K-theoretic computation that comes from thinking of E is a universal object as some K-theory class in our moduli. Right? So if we know one, we know the other, because the Euler characteristic is determined. It only doesn't depend on the sheaf itself. Only depends on its K-theory class. So now that's important. So now it only depends. I only depends K-theory class. If you like the K-theory class of this Euler characteristic only depends on the K-theory class. If we think of this as it's a virtual, both are K-theory classes over some moduli space. And so, so what does this concretely say for dt or pt? Our modulus, our object E. So this E is really a pair. You have the structure sheaf of a threefold mapping to some f, where this f is the structure sheaf of subscheme dt or one-dimensional, pure one-dimensional sheaf. pt in another way, the formula is the same. Formulas are the same. And so then this is, as we deform, this means this stays fixed. This does not deform. So in this object, so in this complex, we don't deform one term. So it means the virtual tangent space is really, the virtual is really the difference. So we take the Euler characteristic of OY and subtract the Euler characteristic of EE. Okay, but then of course the K-theory class of E is the K-theory class of OY minus the K-theory class of F, right? Because this is, okay, it's a complex, but if you think about K-theory, it doesn't matter what the map in the complex is, right? So it just doesn't matter. They're all the same from the K-theory point of view. And so this would say that this is equals to the Euler characteristic of F plus chi of F. So this is maybe a bit more be more pedantically OYF, but that's so. So this is the what is it? This alternating sum of x, but x from the structure sheaf are just cohomology. So this is the same as the old Euler characteristic of f plus the Euler characteristic of f. Oh, and this is kind of third dual object, so one can compute it by third duality. And so then this would be, and then minus Euler characteristic of f. Right. So this is so far there was somehow nothing, no, there's no discussion of localization. What I just said is that if I want to know the virtual tangent bundle as an element in K theory of my modular, here's a formula. But now suppose we have a torus action. Any questions about what I said, or? So now suppose we have a torus action. Acting on threefold y. And let's say that, just for the sake of the argument, let's say this is this has isolated. Let's just, since we have it here, so let's say isolated. Let's say isolated 6 points. And so then we have so this means we have some fixed point, maybe call them red. And then we have some, kind of torus invariant neighborhoods of the 6 points. Maybe this is not the best picture, so maybe I'll try to. Oh, actually, I have the shapes, right? So I can use the shapes. This is one shape, and then I'll take the other shape. I apologize. It just kind of misses. So then maybe these are the torus invariants. These are points, and this is the blue one, torus invariant curves. Joining them. Okay, so this is we will have like bundles over P1, so the picture will look something like that. And so then we can compute. Then of course we can compute this. So this is some Euler characteristics on Y, right? So this means this is an Euler characteristic on Y. And that Euler characteristic we can compute by localization. Right? It's some computation. That's a computation in the K theory of Y. In the current K theory of Y. Right? And so so this is if we compute in the current K theory of Y that only 6 points contribute, nothing else contributes. Right? This is by computing the Euler characteristic of some sheaf, whatever, some sheaf on Y, and Y has isolated 6 points, and only 6 points contribute. Is that clear? And so then I get this T virtual is therefore T virtual is therefore the sum over fixed points of what? Of some quantity. Maybe I'll write it, maybe I'll write some kind of curly T of the restriction of my sheaf to that fixed point, to the chart at that fixed point, to the corresponding maybe Fi, where Fi fixed point where F is the restriction of to the. And what is that? So what is this function? This function is, well, you compute it. So now you compute it. You compute that function. That function you compute for C3. So this, you can imagine that chart is like, let's take we do let's just go back here. Let's copy this thing. So here I have two fixed points. This picture I have one fixed point, and then another fixed point over there. So maybe this point is equals infinity, and that point is equal to 0. Right? And so what would my so this is let's do the infinity. It's easier. Then we we have restricted to infinity is just this part. We just forget whatever. Think of this. This is my kind of F infinity. And the way to think what is that T, and so this F of infinity we can represent in the K theory. So in K theory, in K theory of this chart, which is C3, everything is a multiple of the single kind of box, kind of box, which is the structure sheaf of the origin. And so this is the generator, if you want. Or you can also think, so you can also do the structure sheaf of it's easier, I think, or of the structure sheaf of the whole C3, but then it's somehow, I mean, the formulas look better for people like these formulas better. And that's a preference. And so then this particular situation, that would be this F infinity, would be my generator, which is okay. I'll write it times what? Times I have to compute all the weights of all the boxes that appear in this picture, and all the weights of all the boxes that will appear in this picture are what? So if I have a diagram like that, then the weights of monomials that appear in this are just 1. So this were I remember this has the weights T1 and T2, and then the third weight was Q inverse. So the weights of that would be, so the weights of the functions are dual to the weights of the actual tangent direction. So that would be T1 inverse, T1. So okay, maybe let me draw this in a bigger way. So that would be one. Try bigger scale here. One, T1 inverse, T1 minus 2, T1 inverse, T2 inverse, T2 inverse. Right? That's the weights of the function. So here we put the sum, so it's 1 plus T1 inverse, T2 inverse. And then we get all the functions in the third coordinate, so it'd be 1 minus Q. Right? And then what we do is we take this T and maybe Q, let's take of this, let's denote this Q inverse, since it's the weight of the third coordinate, let's call it T3, since the weight of the third coordinate. And so then this T of F T of F, that would be this T of F. So some rational function now. So T of F would be this F minus T1, T2, T3 F bar, minus 1 minus T1, 1 minus T2, 1 minus T3 F bar. And by linearity, it's enough to check. So this is where bar means Ti bar is Ti inverse, where by linearity, it's enough to check that F of a box, what would that by this formula be? It would be 1 minus T1, T2, T3, minus 1 minus T1, 1 minus T2, 1 minus T3, which is, if you expand it out, will be T1 plus T2 plus T3 minus T1, T2 minus T1, T3 minus T2, T3, which is correct. Okay, and that's the formula behind me. And in fact, since I was preparing this, I was drawing this, I also decided to try my skills in making it move. So now we can. Sorry, this is just for fun. Like, let's see. See, I have to get out of the way, so then you can see it kind of appear. All right, well, I was just for comic relief. So any questions about this formula? And they didn't. So this is. So this says that if I want to know the weight of if I want to know the weight of I want to know the weight of some localization configurations. Okay, I have to sum over all the charts, and then I get this expression. And so then this is you think about it. So this is okay. That's a good expression, except it has a certain drawback, and the drawback is that there is a just some big rational. So this is some sort of in general. There's some kind of big rational function, which is only if you sum over chart, and so only if you sum only the sum over fixed points gives a Laurent polynomial. In particular, in here, so for example, in here, e.g. in here, if you look at this, so sorry, I take it back. Okay, so all of that has this function. All terms here have 1 minus q inverse in the denominator. So it's a slightly unpleasant. So this better idea is to so go back here. Is to single out the contributions. So the better idea is to single out the contributions of pure edges. So for example, for instance, if we want to know, meaning that if we want to know the whole contribution, let's just do it as an example. In other words, we want to know the virtual tangent space at this point here. Right? So the way we computed it from the previous formula, that would be one rational function for 0 plus another one for infinity. And instead, we would like a formula where you first compute this one, where so this means, what does this mean? This means if I have it's really a constant in my twisted bundle. This is a constant map in my twisted bundle. This is a constant section. Of my twisted X bundle. If I have a point which is fixed, so if I have some clutching function which is sigma, and I have a point which is, so this is a point correspond to, so this comes from points. So if I have some clutching function sigma, if I have a point fixed by that sigma, then I can then so there's let me order some sigma my clutching function. If I see here I have a torus fixed point, so but in particular I have any point fixed by that clutching function would give me a count section of my twisted bundle plus a polynomial plus some polynomial, you know, kind of f at 0 plus a polynomial f of infinity. Right? And so the way to define this polynomials is easy. You define the kind of reduced of f. This is you define to be the old one minus the tangent space for this pure the corresponding pure edge. Or maybe this pure edge is this one. So my f restricted to, say, maybe my f0, that is that, well, at 0. This is the same, this is this f of pure edge plus finitely many boxes. And because it's just, so this f was a character, you sum up or you compute the character of all, you sum up all the boxes in this diagram, and the rational function part and that sum is the same. It's the boxes that are different. I mean, there's finitely many boxes. Color coded. Color coded in the picture. And this implies that this is in fact all-around polynomial. And so if you take out this contribution of the pure edge, that the rest is so. So in the end, you take. So if I have a general, I'm going back to this picture I had here. So this is, you imagine there's some kind of pure edge sitting here along the, and this means this sits just right. Pure edge, and then there's a bunch of boxes. Another side. In principle, another side, but for us, we only care about one side. But so this is a bunch of extra boxes. Then the virtual tangent space at such data that would look like the virtual plus contribution, find the contribution from. Okay. And now if I go, and now if I go to our picture here, to this picture. Sorry, this is nobody corrected me that I put the wrong guy here. Well, I'll correct it later in the note. So this is the wrong picture, right? This is in the straight geometry, and this is the skewed geometry. But okay, so this should be this be corrected. So I'll do that later. But now going back here. Try my best to. I'll go back here. There's this picture. The shift by Q. So the boxes zero, they just shifted. Whatever their weight is, that will be just shifted by Q. Right? Well, there are no boxes at infinity. We don't have to worry about them. And so what will happen with the edge? So the edge, the character, the virtual of the pure edge. What would be, how to think about that? Well, look, we have some partition, maybe here. So this corresponds to some point in the Hilbert scheme I took. I write this for a fixed point in the Hilbert scheme, but in principle, it could be any point in the Hilbert scheme. It doesn't matter as long as it's fixed by my one parameter subgroup. So this could be, doesn't have to be fixed by the whole torus. So this is my partition lambda. So this belongs. This is a point in my Hilbert scheme of C2, in this case 5 points, fixed by my sigma. And so in particular, this means that sigma in particular acts in the tangent space at this point to my Hilb. And that character of that pure edge, what's it going to be? If I take this will be a part that comes from. There will be a part that comes from the zero and from the origin. So this is by localization. This will be a part that comes from the zero, the part that comes from the infinity. And here it will be, so this is, you take the character of at the tangents by the Hilbert scheme, but you we substitute the variables with sigma, because this is, the sigma is, well, sigma means in this case, sigma, in this case, sigma is scales one variable and leaves the other variable alone, but in general, some one parameter subgroup, we shifted by sigma. And then here we, and in In the other direction, it's whatever, it's free to move any way you like. So it's going to be 1 minus Q inverse plus on the tangent space at lambda to the hilt. Now it's not shifted by anything, and then minus over 1 minus Q. So in principle, this is in principle some sort of geometric series. Right, because if I have a some Laurent polynomial, I make some change in Q, and then this is going to be maybe all right. So I can write it like that. I can write it as Q times T lambda over 1 minus Q inverse, but now with the minus sign. I hope that's correct, or maybe Q inverse. Okay, that's better. And so and so this means this together, this is I have some polynomial shifted by Q, and then I do something like this, and I subtract and divide by 1 minus Q inverse, so it's the sum of geometric series. And if I'd like to compute what would be the contribution, so the contribution to over. So this is not the symmetrized. So we discussed that it's important to have some sort of symmetrized virtual structure shape, but let's not talk about this yet. Not yet. Maybe not. So if my virtual tangent space is some whatever summation AI has some character I, then our virtual has it's a product of 1 minus AI inverse. Right? Here I get the formula Tvir is summation of maybe some kind of expression, sort of like whatever Wi, maybe still call it AI over 1 minus Q inverse. Then this means that this would be this expression here in the end will be a polynomial. So the way it's written as a rational function is some intermediate step will be a polynomial. And the way to write this polynomial, one can write the corresponding conversion with first write an infinite product. Okay, then most of the terms will cancel in those infinite products, and we'll be left with a finite expression. So this means this virtual would be a product of 1 over, or not 1 over, but really Q gamma function of AI inverse, where Q gamma Q of X is 1 minus X, 1 minus QX, 1 minus Q square X, etc. So this makes sense because it satisfies the simplest possible Q difference equation and has poles at X equals 1, Q inverse, Q minus 2, kind of analogous to the gamma function having poles at 0, minus 1, and so on and so forth. So it's this expression. And so that we conclude that the weight of the twisted edge is equal to the product over all weights in the weights in the tangent space to my space X, and lambda is a point which is fixed by, so this is, I remind you, lambda is a point fixed by my one parameter subgroup. And so this would be, here I get product. Here I get gamma Q of W inverse, and then with the action of sigma, meaning sigma changes variables there according to how sigma acts, and then divided by gamma Q of Q times W inverse. So this is the other part comes from this. So that's this part here that gets me this part there. Right? And so conclusion. Change in sigma affects the current weight. As follows. So it changes the edge of the maybe okay, let me go back here. Sorry, I was here. And the weight. Oh, actually, I need to reorder them. I apologize. To move them around. At some point, the computer becomes tired of this. So, let's see if I can finally wake up. I think it's the file gets long as the lecture progresses, the file gets longer, and it's harder for a computer to maintain a file, and so that means we all kind of. I mean, it's a good thing that we're. I think it's a good thing that we're. Our lecture is only 1 hour and a half long, so the weight. The weight of this thing is the weight of this thing times take a product or all weights in the tangent space to x at my point lambda, and then you put my sigma acting. Okay, which makes sense. So now this means it's a good idea to multiply vertices by the product of if we multiply by this product, then somehow the changes in geometry will be exactly compensated by the action of my one parameter subgroup. So this means this would be a much nicer object, right? And that's, of course, for those of you familiar with the factor, this is kind of like the Iritani class. What it does is kind of counts. This is counts maps from C to space X. So if I would just take all polynomial functions or whatever, or former series from C that goes into X, then the character of that space looks like this gamma function. Yeah, this is completely analogous to the fact that in we have like this instanton partition function in 2 dimensions. And okay, you sum up instantons, but it's good to multiply them by double gamma functions. What do double gamma functions do? Double gamma functions do just the perturbation around like a maps from C2 now. So this is if you have a map from C, then the corresponding character in case here that's a single gamma function. If you have 2 variables, it's going to be like a double gamma function. So that's just completely analogous. It's like a perturbative prefactor if you want into some kind of Nekrasov perturbative prefactor. And what this prefactor does, like I said, this is this counts just maps to X from C, and then or from the formal disk, and that if I take my vertex, I decorate by this object, then it becomes as if my so that would be saying like it'd be like saying that I really make this. So what would that mean? That would mean I'll just take this object. I apologize. That's okay. Finally copies. Well, I'll put it in the notes. So I've probably the computer doesn't want me to copy another image. So there's something else I have to say in the remaining whatever 2 minutes. Probably 2 minutes won't be enough. Is that if we look at this picture, that what would be the z to the degree is just z to the number of boxes, right? So then if I take I had some prefactor, which is, I hope it works now. So sorry, I guess I'm exhausting the powers of my computer. Okay, so you have z to the degree of f, some factor here. Yeah, sure. Question. Yes, great. I love a question.
Did the error propagate again, where these should be the same, have the same edge profiles, or?
Say it again?
Should these both be kind of flat, or one's skew and one's flat on the right side of the diagram?
Yeah, one is skew, one is flat. Yeah.
Okay.
Yeah, and so that means, so if I multiply by this gamma function, it's like I make this thing really infinite. I mean, really infinite. And then this means then there is no difference between skew and not skew. So this is I'll put in the notes, but right now the computer doesn't want me to copy another image, I think. But let's talk about something else. I have z to the degree, and so what was z to the degree is like the z to the number of boxes in this case, you know. and this picture visibly has 4 fewer boxes here. Right? Visibly a lot. Everybody agrees that it has 4 fewer boxes? However you count the boxes in an infinite thing, it's this one has 4 fewer. And you have no objection to that. What that number 4 is? 4 is the following. 4 is, you want to know, again, the degree So what's the degree? The degree of f. What's that? Is you have to compute. What's that? This is you'd like to compute the weight of the determinant f, the fiber at 0. Determinant of the fiber at 0, and you divide by the determinant of the fiber at infinity. Okay? Everybody agrees with that? And so then for a straight edge, this is just by localization. So if I want to do for a straight edge, what would that be for pure edge? This is, if you take, so this is this 4 pure boxes. This is in the pure edge. And so this is will be so if you take like a pure edge straight and the pure edge skewed, they have different number of boxes. So that would be here. The statement here would be saying for pure edge, this difference is just the pairing. You pair with so this is this degree. So this is okay. What's this degree means what with respect to some line bundle. So this with respect to the line bundle of 1 on the Hilbert scheme. So this is really pairing of sigma, which is a co-character, with the weight of O of 1 restricted to my point lambda. That is a character. And so co-characters and characters, they have a natural pairing. And so what you need to do is you pair one and the other. And so where the 4 comes in here? So a co-character here is that T1, T2 equals Q and 1. And what's O of 1? O of 1 is the product of all monomials. In this diagram, so we have this diagram here. The 1, T1 inverse, T1 minus 2, T1 inverse, T2 inverse, T2 inverse, all monomials here. So this would be T1 minus 4, T2 minus 2. And so if you pair these two, out comes the number 4. And so this means it's good to multiply. So conclusion, it is good to multiply vertices by the following thing. So if you take kind of like exponential, or in this case we take log z log weight of 1 divided by log q. Or in general case, if you have more than one dimensional picard, or you take exponential summation log zi times log kind of the ice line bundle over log q if picard more than one dimensional. And so this expression, that is the same. This has the same Factor of automorphy. So factor of automorphy is an old-fashioned way of saying it satisfies an abelian q-difference equation. I think I should say. Well, anyway, it says transforms. If you shift q's, then something happens. Shift variables by q, then something happens. There's the same factor of automorphy as that line bundle. Remember, we had line bundle U, which was that this Poincare line bundle. On Poincare line bundle was the elliptic homology of X cross the Picard cross peak X all times my elliptic curve. So this is where the variables Z live, and this is where the weights of line bundles live. The whole line bundles live there. And so we had in the definition of our elliptic stable envelope, there was this part, there was like it was a polarization part, and there was this part. And this part is well, not this part directly, but the q-difference equation, the abelian q-difference equation that this part satisfies is the same as well. I mean, I didn't really. You can choose or any other expression that has the same. Or so, I mean, you don't have to put the exponential. You can put, or you can put the theta function if you want. You can put the theta of z, theta of O of 1 divided by theta of z times O of 1. That's another way to put it. So we don't. So maybe I misspoke. We don't want the actual exponential. We just want something that satisfies the same difference equation, and the same difference equation is this. Is that difference equation? It's just in Gromwitten literature, people more used to this sort of solution, but it's okay. That's your freedom to choose whatever solution of that difference equation you want. Sorry, this is I've gone over time and I didn't get to the point. But maybe at least I discussed a bunch of technical points. And if you have questions either about these technical points or maybe as to where this whole thing is going, then maybe you should ask them now. Otherwise, well, just please ask questions. And that's less than I wanted to say, but it's more than I have time to say. So I'll stop here.
Maybe this is a silly question, but going back to the 4 fewer boxes, it looks like I could also add 6 boxes. So I don't know. Could I add 6 boxes? Can I interpret things that way?
No, you can't, because it's, you see, this is you think about how this, what do these bundles really do? This box here, you can think of that box here, this box here. This is really the same box as there. It's just really the same. It's not affected in any way, because
Okay.
this is the transition function do something to monomials, right? They say monomial on one side is equal. So transition function rearrange monomials, and they really say what this monomial was. Transition function will tell you that some monomial that was something called something in one chart is called something else in some other chart. Right? But that's in particular the function, the constant functions look the same, calls the same thing. So this box corresponds to the constant function, and the constant function, okay, nothing happens to the constant function.
Okay, thanks.
Sure. Other questions?
Actually, I also want to ask about this picture. I don't really understand, like, is this diagram supposed to be infinite?
It's infinite, yes.
Yes, so on the left and on the right, you've got actually the same diagram, right?
I don't know. I'm not sure what it means to be the same. It represents, it is kind of the same, yeah. But this represents, you think of the bundle that they represent, there's different bundles, yeah.
No. I mean, like, in which direction are they infinite? I expected they're infinite along this.
there's only one direction which they can be interesting.
Yeah.
They're strictly speaking infinite in all directions, but there's one interesting.
Yeah. And but I mean, if you like you didn't, of course, you didn't draw infinitely many boxes, but if you will, as I imagined the diagram, if you will be drawing all boxes, then they're the same. Or
No, of course not the same. I mean, in a way, if you really let me answer kind of both questions at the same time. So suppose I have some ideal sheaf. So both of these are pictures of some ideal sheaf. Okay. So this is so this may be call this ideal sheaf, whatever. So I have some sheaf, kind of I1 and I2. And if I'd really like to know, suppose I take, so the ideal sheaf itself has no sections. Okay, so this is if I have an ideal sheaf, and this is a subsheaf of O, and it has so only section of that could be constant function, but the constant function is not in my ideal, so it has no section. However, if so let's see, 1, 2, 3, 4, 5, 6, 7, 8. So if I take, so what's really written here are written sections of O of 8 or O of 7. So the one, sorry, this is, yeah, I actually, yeah, this was the picture is not great because it should be this length of the two sides should be the same. But let's imagine this length of the two sides are the same. So if I have this picture here, so here it would be 2, 3, 4, 5, 6, 7. So this will be sections. This will be sections of O of 7 times my ideal sheaf. O of 7 and P1. Okay.
so there
And
are
so
only finitely many boxes.
well, I mean, in a way, there's in this. So you can represent not only the ideal sheaf itself. You can represent this. You can think of this as an infinite diagram. That's fine. But if you'd like to give it a sense about the finite size, then okay, then you'll do something like that. You pull back a line bundle from your base, and you take sections of that, and you get a finite length thing. And then this would be. But if this line bundle is sufficient ample, they'll be very, very far away. And then so that, I mean, whatever interesting part of that picture will be very far away. But and so then you can ask the same question on both sides, and then on one side it'll be, one side will be a little bit shorter because you get the other ideal sheaf has less degree. So, and in that sense, it has fewer boxes. Right? The number of sections of any kind of line bundle is given by Riemann-Roch has to do with the degree of line bundle, and that the degree of line bundle will come. So the number of sections of something like this would be, first of all, it'd be a linear function of 7, has to do with the size of the diagram. So there's the rank in Riemann-Roch, and then there'll be the degree. The degree is the constant term. Okay. That makes sense? In general, the Euler characteristic of a sheaf is some linear function of its K-series class. The K-series class of an ideal sheaf has to do with how many times, what's the multiplicity of its along P1, and how many extra boxes it has. And so that's, in this sense, the Euler characteristic of one is 4 times smaller than the Euler characteristic of the other. Not 4 times, 4 smaller, not 4 times, 4 smaller. Smaller by 4.
Thank you.
Sure.
Sorry, so this pictorial equation over here means that weight of this sheaf on the left is weight of the sheaf on the right times this ratio of Q gamma functions, right?
That's right.
And so you say that it's good to multiply by the Seritani class, so to get rid of this denominators, something like this. So like, what is the big idea of multiplying by the gamma class here? Multiplying the vertex, but I mean.
So this is the kind of thing that the object that we want to do is we would like it to be a solution of some Q-difference equation. But the way it's born, it's not a solution of Q-difference equation. It's more of like an intertwining operator between two different Q-difference connections. And one Q-difference connection is this gamma function Q-difference connection. It's a trivial one. So I mean, it's an abelian one. We can just multiply by some solution of the corresponding Q-difference equation, meaning the gamma functions, so to get rid of that. So if you'd like the vertex to really solve Q-difference equation, then you have to multiply by that so that they
I see. So
not an intertwiner between two things, but it's really a solution of some Q-difference equation.
I see. So before you multiply, it does. Okay, because those gamma functions also contribute to. I see. Okay.
Yeah, the gamma function. It's like you should, the way to imagine this. There's some action happens at zero, some action happens in infinity. So the interesting connection lives at zero, so there we shift the variables. But then if we just do that, then there'll be some contribution from infinity, which is this ratio of gamma functions.
So basically,
right.
Yeah, sorry. So basically, this is only for differential equations for the covariant case, right? Because if I think about equation in the Keller variable, then multiplication by gamma class doesn't change the equation, right? So
yeah, it's constant in those equations. It's in
I
those
see.
variables. That's right.
And also this gamma class appears only when you twist, right? So only when you consider covariant vertex with respect to all the covariant variables, right?
Sorry, I didn't understand the question.
So here, yeah, right. So here you consider this twisted vertex, or rate of a twisted diagram, and therefore you get this ratio of gamma functions, and therefore you get this gamma class. So if you consider an untwisted vertex, do you also get some non-trivial gamma class?
So gamma class is our choice. It's good to say. So if I have, I'm saying if I want some good theory, some nicer theory of vertices, it's better to normalize it by this gamma class. That's all I'm saying. So you take them all and you normalize them.
But do you also get it in the untwisted case?
But so what should I say? A vertex by itself, it's some object which it doesn't know if it's twisted or not. So a vertex is twisted means it refers to a global geometry. A vertex is something just defined kind of locally. So if you
okay.
Yeah, so maybe
I
that's
see.
the answer. Yeah, you always it's good to normalize it. All I'm saying. So it's like saying that I take whatever, like a Gauss's hypergeometric function. It starts with 1, and then it goes 1 plus z plus something, right? And however, if I study this expression, I realize later in the day, or later maybe next day, I realize that maybe I shouldn't make the series start with 1. Maybe instead I should have started with some product of gamma functions. And that's exactly that. It just says that there'll be, like, for example, if I ask, so why is it good to start things with products of gamma functions? For instance, like we were, last time, if you remember what happened last time, we discussed that like the monodromy of this Q-difference equation will have some expression in terms of elliptic stable envelopes. Elliptic stable envelopes is in some sense, it's an algebraic expression. And so this means that it's miraculously the monodromy of my equation, which is transcendental analytic object, miraculously is algebraic. But in fact, it isn't algebraic unless I normalize it. Like if I take like Gauss's hypergeometric function, its monodromy is not given by algebraic
from this point of view, I understand.
Yeah, you have to normalize by gamma function. So that's one.
I see.
That's one explanation of this gamma function.
Thank you.
Sure. But it's exact same. So the exact same. For those of you, I don't know, I somehow keep assuming that you have more familiarity with Nekrasov theory than you have with this theory. But in Nekrasov theory, you count infantons, and you get some generating function, and later you realize that this generating function has much better property if I include an overall factor, a prefactor, which doesn't know anything about infanton. It just talks about like a deformation of the trivial bundle, and that deformation, like X from a trivial bundle, basically it computes just like X from a trivial rank R bundle on C2 to itself. So that X would be, since it's on C2, that will be like a product of double gamma functions, And that the resulting function has much better property if I include that if compared to if I don't. And that's exactly the same kind of phenomenon here. More questions?
Also,
All right,
I didn't understand the derivation of the formula behind you. So, like, you consider it only case of one box where all f is 1.
No. So this is the derivation of
It
this
was
formula.
the derivation.
It's immediate from this. So it's a computation. So that formula behind me, it's immediate from this formula. If you compute in the K-theory of C3, K-theory of C3 is a rank 1 module over occurrent variables. So whatever expression you have, it's going to be some multiple of one box, right? And so you compute this expression for one box, and then you're done. And for one box, you can compute it.
But how did you know where to add the f and f bar terms?
Say it again?
How did you know? So you computed this expression for one box. Yeah. How did you know, like, what?
Well, because this. Okay, so this expression. If you look at this, so this is if it appears if I have something computing in the first factor. So x is like Euler characteristic and x and so forth. It's like Holmes. So if I have some expression here, and it appears in the first factor, this means antilinear in this expression, right? So if out of this expression will come f bar, and then so this expression here will give me this f bar.
Okay, so you computed each of the terms in this sum, like
exactly. It just says so this is some bilinear expression in a rank 1 module over my variables, and so that's okay. I can certainly compute that. Okay, well, that helps.
Thank you.
Sure. More questions? All right. I thank everybody for your attention, for your questions, and I'll see you in a little over half an hour in the seminar. So but this is all for today.